Hi, everyone. We'll be starting fairly soon in the next few minutes. Right, folks, thank you for being here. This is a really interesting topic for several of us in the room. And I really want to thank our speaker tonight, Rui Fernandez, who is here presenting. He came to visit us in Wits Geosciences 2 years ago to do an internship while he was doing his master's at the ENS in Lyon in France. And we devised this particular project, which has turned out to be really interesting. And Rui is currently doing a PhD to the University of Toulouse in France, but he's working partly on South African fossils from the cradle of humankind. So afterwards, I'm sure you can talk to him more about his PhD work, but this is just I think a 3-month internship that Rui did with us and with Nonku, in particular on the TEMA. So Rui, over to you. I'm just going to hide these controls and get you a laser pointer. And it's all yours.
Thank you. Thank you for being here to listen to my presentation. As Grant just said, this was mostly done 2 years ago. It's, as you can see, it's a study of fossil diagenesis using automated mineralogy. To explain what all this is about, I need to talk a little bit about fossils. Okay. First of all, don't know you, when I was a kid, fossils was something really funny, but relatively static for me. For me, the research in paleontology it was, first of all, to find fossils. That's the funniest part. You give the names, etc. Yeah, we're all happy. Then probably I imagine some studying, measuring them, drawing them, doing stuff with it, and then pretty much just putting them in a museum. That's so they would look nice. Then I got to the university, specifically to the ENS de Lyon, France, and I discovered a thing called geochemistry. And I discovered that fossils are actually quite used in geochemical studies because they can reveal a number of things. For example, they can use to reconstruct the ecology, the way of living of a living being. Here, for example, you have some fossil teeth of Australopithecus africanus. They are from near here, from Sterkfontein, maybe you know, from the cradle of humankind. And the thing is, this study looked at isotopes of lithium, calcium, and barium in order to reconstruct the age until which the babies drank their mother's milk. And this is just one example among others. Something else you can do, it's nice, it's to reconstruct climate or environment. For example, here you have a study that looks at carbon and oxygen isotopes in order to reconstruct the composition of the groundwater in which those fossils were buried. Then something else very cool you can do is to trace their geographical origins. You can do it with trace elements, but also, for example, with strontium isotopes. Here is another example, actually, from the cradle of humankind. You understand that's one of my subjects of interest. And some researchers try to found teeth bones of rodents that were collected by raptors in caves. And then using strontium isotopes, they try to find out from which terrain they came from. And something that is less used, but it's one of the things I will study in the future as well, is that fossils can be used for dating as well. A classical way is fluorine that gets more and more abundant in bones and teeth as they get older, after the death of the animal, of course. But more recently also, the people have tried to do uranium-lead dating based on the accumulation of uranium in those teeth. So this is very, very, very cool, but we have a little problem called diagenesis. Diagenesis, it's all the physical and chemical alterations that happen after a fossil, which is not a fossil yet, is buried, and until it's exhumed. They can be interesting on their own, but they can be more or less extreme. For example, one relatively soft way is that you can have substitution inside the minerals. I told you about the fluorine is because the main mineral of bones and teeth, that's hydroxyapatite in vivo. But then as the fossils get older, the hydroxy is replaced by fluorine. So it becomes fluorapatite. Always in apatite, the substitution that can happen is that you get hydrogenocarbonate ions that replace either hydroxy or the phosphate ions. Then a little more extreme, you have large-scale contamination. Here is another example. These are not from the cradle of humankind. This one is from the west of the Lake Turkana, from northwest Kenya. It's a famous fossil, the black skull, from a fossil hominin. And you can see it's black because it has a coating of manganese oxide, which is black. And then you have the extremist of extremists. You have fossils that have those mineralogy has nothing to do with the original fossil. You have, for example, ammonites, whose shell is originally made of nacre, which is aragonite, and then you can randomly preserve them as pyrite or calcite or something else. You can also preserve them in aragonite, but it's rare. They are sold for very high prices. The aragonite ammonites. Anyway, so it's important to study the mineralogy as well as the chemistry, but most importantly the mineralogy, so the real mineralizations of the fossils after they were buried. And there are several ways of doing that. Mostly it's actually done indirectly. There was the searchers actually look at the chemistry, for example, with X-ray fluorescence, scanning electron microscope, and then energy dispersive X-ray spectrometry, or EDS. You can use bigger tools like a synchrotron. You can use a laser ablation mass spectrometry, things like that. Yeah, for example, here you have it's another hominin fossil. These are teeth and bone from East Africa. It's Homo habilis, and this was reconstructed with microcomputer tomography, and this bright segment that was isolated, and they wanted to know what it is. They did some XRF, X-ray fluorescence, and they saw that was high barium, high sulfur. Okay, it's barite. That's what they used, but it's done by hand basically. Then there are other ways to more directly see which minerals are present. One is Raman spectrometry, which was, for example, used for looking at minerals in bacterial mats. Another very cool one that's kind of gaining momentum is X-ray diffraction, which is the idea that you have an X-ray that goes through your mineral and it's diffracted in a characteristic way that allows you to recognize the mineral. Here, for example, you have a study that has these are not hominids; they are early tetrapods, and they have tried to reconstruct the mineralogy. One cool thing about this is that it also gives information about the orientation of the crystallites. And it also has the advantage that it can be combined with X-ray fluorescence. So you have this, for example, this other study when you have two detectors. This was actually done in a synchrotron. You have two detectors, one for X-ray diffraction, it shows the minerals, and the other is for X-ray fluorescence, and it shows the chemistry, basically. But doing things like this, well, you need big equipment. In this case, it was synchrotron. Not all of them use a synchrotron, but it's several of them do. And in any case, there is no simple way right now to get in one measurement both chemical and mineralogical information. You have to combine two techniques, or you just measure one, for example. So here we wanted to try a new method to look at mineralogy and chemistry and for diagenesis in fossils, and it's scanning electron microscope automated mineralogy. So here's the principle. Basically, it starts with a scanning electron microscope, and you have an electron beam that hits a mount with a sample, which is has a flat surface. It can be either an epoxy block, an epoxy resin block with the sample inside, or it can be an uncovered thin section. Then you have backscattered electrons, so BAC, that give you information about the average atomic number, and this allows you to basically, the higher the atomic number, the brighter. So it allows you to see which are the main parts, the main grains, the main segments of your sample, and then you have an emission of an EDS spectrum again, and that gives you the elemental composition. And so that way you can get backscatter electron maps, elemental maps. This can be done also with a normal SEM, but the thing about the automated mineralogy is that you have additionally a database of minerals, specifically of EDS spectra, for many different minerals, and from the chemistry that you've calculated from the spectra, you can recognize the mineral. You can attribute them to a certain mineral. Of course, the bias of this is that you cannot distinguish minerals that have the same chemistry. I don't know, calcite and aragonite, it's the same. But anyway, so I wanted to try this method, which has previously been used in the past. It's mostly developed to search for metal ores in rocks. It has also been used for other industrial purposes, such as analyzing waste ashes, typically. It's also a little bit used in archaeology. We're getting closer to trace the origin of certain ancient potteries, but it's not been used in paleontology yet, nor for any other biological object for that matter. It's been used a little in sedimentary rocks with microfossils inside, but it's not the same. So what we wanted to do is precisely this. Look at if we were able to do automated mineralogy on teeth and bones. And first of all, we wanted to look at modern teeth as a reference to know what to expect from the fossil ones. And then we wanted to look at fossils with different ages from different environments to have an idea of what the automated mineralogy can show. And then the objective would be to try to link that observed mineralogy and chemistry with the diagenetic conditions that those fossils belong to. And finally, there's a last thing that it's more experimental that we wanted to do is test the robustness of automated mineralogy on slightly irregular surfaces. This is because we had some very precious fossils that I will show you that later that we didn't want to grind them to a very smooth surface because that would be a destructive analysis and we didn't want to destroy them further. And so we put them without grinding them and we tried to see if it would work. Spoiler, it works. So type of method, the machine that we used, it's a test scan integrated mineral analyzer, or TIMA, which is actually located here. Then the samples, the modern samples that we use are human and crocodile teeth. And as for the fossil samples, we had there's a few different things. There's the moderately old, which are hominin teeth from the Swartkrans cave, always from the cradle of humankind. They are early Pleistocene, and yeah, you must imagine they are 1 or 2 million years old, maybe a little more, not much more. And then we have much older fossils that are therapsid and one dinosaur, mostly bones and some teeth, from the Karoo Basin. And they span from Upper Permian to Lower Jurassic. So this implies that I'm presenting them as a group, but really they are not, because between the oldest and the youngest, there's something like 100 million years. So, okay. So the other problem we had that we didn't want to polish the surface of the hominins because they're very precious. Actually, all the fossils that we use here, they were previously cut for other studies. Some of them were either sampled, you will see, but we didn't want to damage them even more. And specifically the hominin teeth that are super precious, they were cut in half, but they were not mounted in epoxy or in a thin section or anything. And we wanted to try to put them in the TIMA anyway. So what we did is we invented a little something, removable mounts. Basically, we put little plastic caps that the teeth can fit in, and we mounted those in epoxy blocks. So you see here, this is actually that. And then we stuffed the bottom of the caps with those little buckets with aluminum foil. We also wrapped the fossils in aluminum foil. Here you can see them. And then we put them we accommodated in the buckets, taking advantage of the little flexibility of the aluminum. Sorry. And we tried to put them as flat as possible and as flat and as horizontal as possible because the machine needs a flat surface. Was certainly not as perfect as when you grind them, but we tried it anyway. See if it works. So let's move on to the results. First of all, as I said, the first step in automated mineralogy is to look at backscattered electron maps. So here you have a human, here you have a crocodile. You distinguish them because one has a lot more enamel than the other. This enamel is the top part of the tooth. And one thing you can see is that you can already distinguish enamel and dentin from the backscattered electrons. The enamel is brighter, so it has a higher average atomic number. We'll see why. And so, okay, that's a first thing. And then one thing we can already notice, and one of the little problems we had, is that sometimes, not always, but sometimes the dentin is not completely mapped. So here you might imagine the pulp of the tooth, but in theory, and this crocodile tooth, the teeth should continue a little bit like that. You see a spot. Why is that? Probably it was not bright enough, possibly because the dentine contains some organic matter, so it didn't shine and backscatter enough electrons. The threshold we put to not map the resin was 10%, and probably this was under the threshold. So yeah, a little problem like that. With this, I'm showing you a crocodile tooth, but we also had the same for a few human teeth. So besides this, once we have a look at the backscatter electrons, we can look at the elemental maps. So again, it's possible to distinguish the enamel and the dentine in those maps. It's of course less visible on the crocodiles because it's thinner, but it's still there. And something we can notice is that calcium is typically more abundant in the enamel, where the magnesium is more abundant in the dentine. You can see here. So this, by the way, might explain why the average atomic number in the enamel is higher and therefore brighter in BSE. And the other thing that you can notice already is that crocodiles are more calcium poor than humans, and it's the opposite for magnesium. And the other thing that we noticed is that there can be zonations, elemental zonations, but only in crocodile teeth. You can see in the dentine that you have this relatively calcium-rich zone near the enamel-dentine junction, and you have this poorer zone, and then near the pulp, it's rich again in calcium, and the opposite for magnesium. We'll try to see why, but just one notable sample, there's only one of them. It's also a crocodile tooth, but it's much bigger than the others. And it's that one sample, we can see much more spectacular zonations with those layers in the teeth, in the tooth. It's only one of them. So after we look at the backscattered electrons and we look at the elemental maps, we can move to the mineralogy. And as you can see, it's extremely boring. Why? Because, well, it's almost only apatite. It's over 99% apatite. You can also see that we cannot see the difference between the dentine and the enamel anymore. They are shown to be the same. Here you can, it's a little broken, so you can kind of guess this is the enamel, but you can't really distinguish it from the dentine, and same for the human. The other notable thing, we saw by quantifying the elements in the samples, is that they are quite fluorine rich in weight percentage, 3.76%. And I tried to calculate the stoichiometry compared to the apatites, and that would mean that this is fluorapatite, which is strange because in theory, a biological apatite is hydroxyapatite. And yet here we feel as if it was fluorapatite. So strange. The other thing that we notice that there's pretty much only one other mineral besides apatites, it's calcite, and there's less than 1% of it. So it's very hard to see. I put some arrows so you can see there's some little spots over here. Yeah, very hard to spot. You have to zoom very hard. And the interesting thing is that they are mostly located within enamel, not only, but mostly within enamel. And so actually you can kind of see where the enamel is or where it's not because of this calcite. By the way, do you remember that I told you that the crocodile teeth have thinner enamel? When one of logical implication is that calcite is less abundant in crocodile teeth than in human teeth. Okay, this is what we can expect from the modern teeth. Now let's move on to the fossils. First, the moderately old, the hominins fossils from the cradle. First of all, we can see that the slight irregularities we had, they are generally mapped. Especially, you can see especially on this specimen, I don't know if you can see, but there are some striations that were left when the tooth was cut. It was not trimmed then, so it's not smooth. And those little arrows show the direction, and they are kind of visible on the backscatter electron map. But then there's no problem. These are 4 different teeth. Just for information. But anyway, there's no problem to map it as apatite or whatever. The mapping is done correctly. There are bigger irregularities that are not well mapped. There are holes. Here you can see that those 2 specimens have holes that were drilled for probably geochemistry. I couldn't find the exact publication, but those appear as little shadows. Then there is this one specimen that I was cut in a strange way, so that it was left with this rectangular ridge, and the top of it is kind of visible and it's mapped. But on the sides, when there's this very harsh slope, then it's not. It appears as a shadow again. It's not mapped. Then you have those slopes as well, because you have the the tooth in 3D that continues underneath, and there is no epoxy here to block the beam of electrons. So you have those things here that are interior the same material, but you see they are shaded, and the TMA cannot recognize them. That's normal. It's there are irregularities that are too large. But the little ones, they can still kind of be mapped. So yeah, good thing. By the way, this is also below the focus surface, and here again, you imagine the tooth. So those were not mapped. The other thing that we notice that the aluminum foil with wrapped the teeth in, that can actually be ignored for the analysis. Here you see some little spots of the aluminum foil, and at the beginning, why it has this squared border is because we wanted to avoid to point the electron beam at the aluminum foil, because we're not sure how it would react. It did not react at all. It went perfectly. And we realized that afterwards that we can simply ignore this phase. The TMAC has a spectrum for aluminum metal. It can recognize it. But if you simply don't put it in your library you're working in, it's going to be unclassified, and you're going to ignore it. So for the next time, it's good to know. Then besides that, in terms of minerals, it's still over 99% of apatite. So not so interesting anyway. But there is a little new thing. There's a little more other minerals, especially one phase that I will talk about later. Well, there's regular calcites, there's a little quartz, and that is manganese-rich calcites that you can see here in dark purple. And by the way, you can notice that, unlike in the modern teeth, these calcites, the quartz would be somewhere like here. It's I can cross it, but the calcite is mostly within the dentine part. Which is logical. It's more porous as well. So it's a very well-known thing that enamel is better preserved than dentine. And the other thing that we can notice that the enamel and dentine are less distinct than with modern teeth. In backscattered electrons, it's a little more blurry, and especially with elemental maps, the limit will be in somewhere here probably, but we cannot really see it. Here you can kind of guess it, but it's not very clear. You remember the modern teeth, it was perfectly clear what the limit was. Here is not so much. So interesting to know. So this is what is moderately old. Now let's get to the very old. The Karoo fossils. Here you have 4 of them. We had more, but just to show this one. So this, sorry, I have to ask you to remind the names. This is a Bauria from Lower Triassic. This one especially is a Thrinaxodon, also from Lower Triassic. A Procynosuchus, Upper Permian, and from Lower Jurassic, a Lesotosaurus. This one is a dinosaur. and you can guess where it comes from. So first of all, we notice that within the apatite, there are now large calcite field porosities. The bone is much more porous than the teeth, and yeah, it's mostly filled with calcite. This is actually a dentary, so it's a lower jaw, and you can see that there are teeth, and they are less affected than, besides the pulp, kind of less affected than the bone, which is already porous. There are some cracks with calcite, but mostly you can see the whole tooth base. So besides that, then there's this phase that was very hard to map at the beginning, manganese-rich calcite. At the beginning, the machine was not even able to map it, actually. So I had to look at we had to look at the spectrum, the ADS spectrum. It looked like calcites, except it had manganese. So we defined this new phase. It's for that we defined it. There are basically two specimens with this phase. One is this one I'm showing here, and then there's another one. I tried from the calculated abundance of manganese, and supposing it would substitute for calcium, to calculate what would be the stoichiometry of this phase, and it appeared to be something like this. Okay. Then you can see there is a diversity of silicates. On the crater fossil was a tiny piece of quartz all alone. Here you have silicates. They are mostly superficial incrustations, as you can see here and here. But in some cases, especially in one case, they can get quite deep. You can see this one, the Procinosuchus. You can see it has in its porosity very well stuck piece of orthoclase. It also has some quartz and some biotite over here. Generally, it's the thing that's more abundant is quartz. See here and a little bit there. Besides that, few oxides, so probably not very oxidant condition. There is a rutile here incrustation, but besides that, not a lot of oxides. Besides quartz, of course, which technically. And anyway, and then there is one specimen, the dinosaur, the youngest one, with diagenetic barytes, which you can see it has filled these cracks, and that's barytes. Okay. Now let's discuss if this worked or not. Well, first of all, the modern teeth. One thing we can say that enamel and dentin are very well distinguished, and this is actually quite normal. It's known that there are variation of chemical composition in the enamel and the dentin, and in particular that the enamel is more rich in calcium. As you can see in this other study on human teeth. Okay, that's perfectly normal. It works. Then there's the problem of why we seem to have fluorapatites instead of hydroxyapatite. One simple explanation that comes to mind is toothpaste. Because toothpaste is rich in fluorine, that's made to strengthen the teeth. And so maybe by brushing their teeth, since they are modern teeth, by brushing the teeth, maybe they introduce some fluorine. The problem is that I doubt the crocodiles also brush the teeth. And we also have the same fluorine content in the crocodile teeth, absolutely no difference. So probably not that. One problem might come from the calibration, because the SEM is calibrated on a manganese standard, and maybe that's not the most appropriate for accurate measurements in biominerals like this. But maybe we should try apatite or something. But besides that, the explanation that came to my mind is that SEM simply cannot detect the lightest elements, including hydrogen and therefore water and hydroxide. So maybe it was actually hydroxyapatite, but because it couldn't see the OH, maybe there was actually a very little fluorine, but by mass balance, it appears as if there was only fluorine within the apatite. So maybe that's why it appears that as fluorine, as fluorapatite. Then we have to explain the zonation in the crocodile teeth and why they're only in the crocodile teeth. The explanation that came to my mind is that we have a better temporal resolution, basically. So some chemical variation can be due to daily stresses or variation in the environment, especially in the drinking water. And the thing with crocodiles is that they change teeth many times in their lives, at least some 50 times per crocodile. And so they grow very quickly. And so maybe we can see those donations simply because we have a finer record of the variation of the crocodile's environment compared to a human when it's slower, so it's stacked. It's all stacked. And one additional evidence for that is remember the very big crocodile tooth with spectacular zonation, where that you can add to temporal resolution, also spatial resolution. You have a very big tooth that will quickly, and so you can finally record these elemental variation, calcium and magnesium. So now let's move on to the fossils. First of all, the hominin teeth, which are the moderate old. So the first difference is that, as I said, dentine and enamel are not well distinguished. And we need to explain that. First of all, one possibility is that there was no calcium magnesium difference between the two to begin with. This is highly unlikely. And both the humans and the crocodiles we studied, there was a difference, and there was also there's also in other studies. So there must have been some elemental difference between the two at the beginning. So it cannot be that. The other possibility is that for mapping elements, scanning electron microscopy is less accurate than, for example, laser ablation mass spectrometry, which is used in this study I showed at the beginning. And here they can really see the difference between the two in a fossil from the same conditions, the same age, and so they can map the isotopes very well. So probably there's a less accurate machine. And then this is not completely satisfying as an explanation, because again, in the modern teeth, we were able to see very clearly the difference between enamel and dentine. So probably there is still some blurring between the two, maybe some exchange, some reequilibration of those two elements. To what extent our data probably not precise enough to know it, but probably there is still some transformation. So the other thing that we noticed with fossil, that small irregularities were handled. So that's very good news. The other thing that we can take home is that the aluminum foil can be ignored. You just have not to map it. And overall, they give the impression of moderate diagenesis, because it was still mostly apatite. You saw it in a cave environment, and it can very well be related to a cave environment, because there's more calcites. Okay, that's karstic caves, normal, and you also have manganese. And in the cradle, in the caves of the cradle of mankind, it is known to have manganese. If you have stains like that, so it's typically what you would expect. A little silicates here and there, a piece of quartz, and yeah, that's pretty much what we would expect from a cave like that. Then we move to the old ones. Well, so you notice that the contamination, the diagenesis is much more extensive than in the human teeth, the hominin teeth, and generally speaking, that can be related to a floodplain, fluid plain environment. But we have to see them one by one, because we need to relate them to the Carew stratigraphy to see what we can say more precisely, because they come from very different ages. So I'll be focusing between late Permian and early Jurassic. So mostly the Beaufort group and the Stromberg group here. Let's see by one by one. First, the oldest. There's a zone called the cystocephalous zone in the Beaufort group. It's from late Permian, and it's a sinuous river floodplain. It has massive sandstone channels, little argillous clay interbeds with where fossils can be found, but mostly massive sandstone. And here's that when the Procynosuchus fossils come from. You remember the one with the big orthoclase in the middle? And it's consistent with this sedimentology because it's heavy silicate contamination that's penetrated the bone. Then the more recent, early Triassic, we have the Leistrosaurus zone, always from the Beaufort group. It's a braid plain with silt, mudstones, so a little more calm. There are calcareous nodules that can be related to a paleosoil. It's a more calm environment. And from this zone, we have three fossils from the same species, Thrydax non-Lioneus, and they are all very rich in calcite. It's consistent with this paleozoid with calcite nodules. One of them, the one I showed you, is very rich with manganese. I cannot really explain why. I have not read of especially manganese richness is in this zone, but it can be a specific condition of the zone of the area where this fossil was found in the Newcastle district. If someone knows the geology of that place specifically, let me know. And the other possibility that it has been contaminated with manganese-rich fluids from other strata. Then a little younger, there's the Cyanogatus zone from, sorry, it's early Triassic. It's an arrow here. It's just on top of the Lystrosaurus zone. It's a fluvial lacustrine environment with laminated sandstone. It had nodules of ferromanganese, more in the north of the Free State. And then the more you go to the south, you get more calcareous nodules. There's also hematites and calcite incrustation on some fossils. And what we have from here is the borea. You remember the dentary, and the one that I didn't show you, the diademodon, that is very rich with manganese. It has a lot of manganese calcite. So it's heavily contaminated with manganese. It comes from the Free State. Oh, wow, that's surprising. So maybe it was contaminated by these kind of nodules. The other one is at a little less manganese. It comes from KwaZulu-Natal, and that's from that zone. I have not read that it's specifically rich in manganese. So okay. Then there's the youngest one, the dinosaur from the Masospondylus zone. This is from the Stromberg group. Okay, I inverted the two. This is early Jurassic. Sorry. And it's specifically from the Upper Elliott Formation. It was found in Lesotho. So here you see the Elliott Formation, the Upper Elliott Formation, and here's where the fossil comes from. And it's the one that has barite, you remember? And this one, I found no evidence of barite in the Elliott Formation. However, there is barite in the Clarence Formation, this one, of the Eastern Cape in the form of evaporites. So it's like just on top. And in KwaZulu-Natal, there is the Molteno Formation that is just beneath the Elliott Formation that has pyrite nodules with some pyrites. So my guess is that it probably was contaminated by fluids from other strata, either from below or from above. So as a conclusion, I would say that overall, SEM, automatic mineralogy, was able to give us quite relevant diagenetic and taphonomical information about the minerals in those fossils. That is generally quite a method that is quite simple to use, and so hopefully it could be used in the future to check for fossil diagenesis. The only thing that you have to cut the fossils, but not necessarily to grind them. So that's good. So it requires, as I said, a flat surface. So it's destructive. Fortunately, most paleontologists that work with fossils, they don't care at all about preserving fossils. There are lots of fossils that are already cut, and no one cares, and people keep cutting, and the curators are desperate. And so it can already be applied to many fossils that are already cut, as we did. And again, so the surface doesn't need to be perfectly flat, even a little uneven, and it can still be mapped. So this makes us wonder if we can map actually flat fossils, because there are also fossils like that. So here we use a TEMA, the machine we use is a TEMA, but there are other options for automated mineralogy and other softwares that are not necessarily packaged with their hardware. The TEMA there's a TEMA software and the TEMA machine, but there are others that can be not necessarily reduced with several machines. And this makes me wonder, but it's a perspective for the future. I don't know if it's possible to use those kind of softwares to process EDS maps that were previously obtained on other studies on fossils to try to map the minerals as well. So thank you so much for your attention, and if you have questions, please ask.
Okay, do we have any questions for Rui in the audience or online? If you're online, you can just raise your hand and we'll let you speak. Any questions in the audience? Nonka, I'm coming to you with the microphone.
Thank you, Rui. This was very nice. I'm just interested to know, what about the other fossils that show more variety? Do you have element maps of those?
Sorry?
You know, the other fossils that show different minerals in them. Like you have more calcite, which is more manganese and silicates. It would be nicer to also show the element maps. Do you have element maps?
Yes, I understand. I have not put them here, but yes, I do have element maps of those, and yes, it can be very clearly seen that, especially in the silica map, that those silicates shine very bright compared to the calcite, the apatite. I have those. I just didn't show them.
Thanks.
Thanks for the talk. I was just wondering if the way that you picked the samples, the fossils to analyze, if you have any sense of what sort of rock type they came from and what that rock type's composition was like, especially in terms of the diagenic features that the host rock had undergone.
Sorry, which
well, just in terms of the way you collected the fossils or picked the samples to analyze from the museum collections, I guess.
Yes.
Do you have any sense of what the host rock that they came from is in terms of sandstone or shale? Or
unfortunately, I was not able to find data about the specific locations these fossils came from. For the other one, the hominin fossil teeth, those I knew that they came from a specific cave, and even I know the members. But those ones, besides the Lesothosaurus here, that I was able to find the paper of the discovery, the others I was just able to know the biozone they came from. I was not able to find the specific place. Yes, and indeed in diagenetic studies in general, the people would analyze the sediments that go with it at the same time. Here I didn't have them, so that's why I had a relative generic discussion about those conditions.
Anyone else in the audience here? If not, then we'll start with. Let's ask Lou. You come through and unmute, and then we'll go to Abdullah.
I'm wondering where the fluorine comes from in your ancient teeth.
The fluorine in the ancient teeth. Well, if the fluorine is already observed in the modern teeth, in the ancient teeth, there's definitely fluorine as well. simply because fluorapatite is more stable than hydroxyapatite. So with time, it's replaced, and it comes from water, from the burial environment.
In modern teeth, we don't have enough fluorine, so we have to add it either to the drinking supply or to toothpaste. So I'm wondering if there's variability in fluorine in your ancient teeth. Does that mean the amount of fluorine in the water is changing by some process?
Well, first of all, I wouldn't trust a lot the fluorine measurements anyway, because you see in the modern teeth, they are supposed to be hydroxyapatite, even if with the toothpaste, because you see crocodiles don't brush their teeth. They're supposed to be hydroxyapatite, and then we still see a lot of fluorine. It's not supposed to be so high. So I wouldn't trust that measurement anyway. That being said, if there's fluorine in the water, that you don't need to have much. It's a known thing that the fossils slowly accumulate fluorine with time. So for very ancient fossils, I don't expect to really to find a lot of hydroxyapatite.
Thank you, Lou. And we'll ask Abdul to unmute and come through.
Thank you so much, Louis, for the presentation. I'm just wondering if this technique can be applied to study the paragenetic sequence of events that happened during the fossilization process.
Then, well, you will have to have a relatively complex sequence of events. My guess is that you can. I honestly didn't try to go that far, but well, let's see the fossils. For example, this Lesothosaurus, you have some cracks and then some filling with calcite and then silicates. And with the technique, you can see the elements, the minerals that are here, and then you can start to think about what came first and what came later. For a relatively complex fossil like this, it's probably possible. That being said, I'm not very good at this kind of things, so we didn't do it in our study. But I see no reason why it wouldn't be possible.
Okay, fantastic. Maybe Rui, I can end off with one last question if there aren't any others from the audience. Yeah, I think that's just an old hand from Lou. And so, for me, what's really interesting is in the context of isotopes and old teeth, right? Like dinosaur teeth and therapsid. So do you think what you're showing, for instance, on this slide is suggestive that as long as you don't drill too deeply into the teeth, you are able to still access the enamel and therefore its isotopic composition from when the animal lived?
Well, the this isotopic composition of ancient teeth and even bones, actually, from the Mesozoic is still is used anyway. I didn't show it, but I have in mind a study of about that showed with the oxygen isotopes in Spinosaurus bones that they were semi-aquatic creatures. So that can be done anyway. With this technique, it's just we would just allow to probably avoid some big mistakes. So some areas that are rich with very tiny crystals of other minerals that would contaminate your sampling, and this way you can kind of avoid them and go for the cleanest part. And then, of course, we can also help with the elemental maps. If you see some areas that's more blurry, more suspect, then you can also avoid them.
Okay, fantastic. I don't think I see any other questions online or in the room. So Rui, thank you very much once again. That was really interesting and a nice integration of different techniques spanning geochemistry and paleontology. So that's really fantastic. And next week, we're actually going to continue the paleontological and sedimentological theme because Emma Shea Bordy from UCT is visiting us, and she'll be talking about logging the dust that Centaurus kicked, which sounds like an interesting title. So join us for that, and we'll see you all next week. Thanks, everyone.
Reading my